The dynamics, comes to us from ancient times. The notion of dynamics are inspired by celestial firmament. And what the ancients did, the celestial firmament, if you don't look very carefully, looks very periodic. I mean, they saw planets going against what for them were fixed stars. And by the time they got very sophisticated by the beginning of the common era, a few thousand years ago, they had very sophisticated theories which have now discouraged much, but I appreciate them a lot. So they had epicycles. So they could describe the motions of planets and predict what there will be by summing various periodic motions. Today we call this perturbation theory. At that time it was called epicycles. So their ideas was that at least the celestial firmament was a regular God-made clockwork. Maybe our world was not so regular, but at least there was something regular in this world, and much of the religion has to do with this regularity of the firmament. And today, since Newton and people like that, we are taught, we are taught that the solar system obeys celestial mechanics or Newtonian mechanics. And it does it to very high accuracy. You don't need special relativity or anything like that for that. And that if you specify positions of all the celestial bodies, the planets and the sun, etc., if you specify their instantaneous position and their velocity, these two things put together are called phase space. If we talk about coordinates momentum, we can predict the future as seen in the mirror. Now, this didn't work even for Newton. So Newton spent lots of time trying to explain motions of the moon, that three-body problem, but that turned out to be a very hard problem. Already for Newton, it didn't work very well. But, imprinted in our education is the idea that this is obvious, that that's how the world should work. Classical mechanics is obvious, quantum mechanics is mysterious. I don't get it. But observationally, seems to be true that planets, if you specify positions and momenta, you can, as initial conditions, you can evolve this using Newtonian mechanics. And in this case, you think of dynamics. Now, dynamics itself is a weird word. It was actually introduced by Leibniz. It's a Greek for power. Somehow through the Leibniz lens, it got refracted into the emotions. So today we think of dynamical things as being motions. So dynamics has a space, which is a phase space. It's not this three-dimensional thing about the positions and momenta of the planets. So it's a multiple of things. And it has a law of nature, Newton's law, and that law is immutable. That's how the world works, the celestial world works. Now, in dynamical systems, we actually think of much larger class than just mechanics. So I will use expression phase space to mean phase space of mechanics. And I'll follow control engineers in saying in the general dynamical system, meaning there's some we have a state space which could be discrete. If you're a Wolfram, it's a discrete state space. If you're us, not so computer, in fact, then it's a continuum of possible configurations of whatever you're looking at. And then we are really only at the beginning of the 20th century because for us time is separate from space. So everything that will be covered in this course is, there is a space, state space. It could be amoeba or it could be chemicals, it could be all kinds of weird stuff. It doesn't have to be mechanics at all. So that's why I make a distinction between phase space, state space. State space is more general, and then you're given a law. So laws, the general dynamical system is described by specifying a state space. We'll call curly M, and this M hints to the fact that usually state spaces are not just Cartesian spaces that you live in this room in, but they're usually manifolds. So there's a smooth thing. For example, again in mechanics, if you have something that has 2 degrees of freedom and preserves energy, then the motion is on energy shells. It's not on a restricted to manifold. So that's and now state space is configuration. It's a bunch of labels. So represented the point. X. This shorthand for x1, x2, x3, some number of coordinates. D, where D is in most textbooks. This is D is 1, 2, 3, and in real life, D is in this building in 100,000. And if you're interested in things like fluids and other kinds of fields, defining or space, it could be infinite. The main point about this dimension is that it's a sufficient number of points to specify state uniquely. So, saying the temperature in Chicago right now is minus 28 degrees Fahrenheit, it's anecdotal, but it doesn't describe Chicago. You need, many, many more points to describe the state of Chicago. So, usually a subset of these things is not enough to specify the system. And then we need a law of motion. We need a rule. So we need something that describes dynamics. A motion in this space. It's a rule which tells us that if we start someplace, we end up someplace else time field. And if we have complete specification of states, and we have a rule that gives unique prediction to each state, then we have a deterministic system. And that's defined by specifying state space and specifying the rule of motion. That's dynamical system as defined today, either in mathematics courses or in this course. So whatever you do, you have to describe what is the world that you're acting on, and you have to describe how you're acting on it. Then, to make things possible, workable, you tend to be interested in smooth dynamical systems.
meaning that any number of derivatives of the law of motion can be taken. That's not strictly speaking necessary, so especially for dynamical systems, only have few derivatives defined and the rest is discontinuous. At the time, yes?
Wait, so you're saying that in general we would expect like a C infinite differentiable manifold?
Physicists feel most comfortable with C infinity because we like things to be
Well, we like things to be analytical.
analytical. Yeah.
Okay, so
Now,
but we
that's
don't really.
the real dynamical systems. People who do this in that department tend to look at much sicker systems than they will look at. They can think of dynamical systems which are not with differential, but we will not do this. And our excuse is that the things that we are describing are either smooth, either for our resolution being finite and then real smooth, or smooth for all practical purposes, or they maybe have some countable number of singularities, etc., that we treat separately. So an example might be if you're looking at the billiard and you send a point like ball, which I can go. If you send it in here, then there is a deterministic law of motion that says we're going to end up with specular reflection. But if you send a point-like particle into the vertex, you might not be able to define on this singularity what happens. That's okay, and that's actually quite useful. Very often we need this kind of singular structures to help us organize the motions. In this particular case, if you did a little bit to this side, you go that way. You do this way, you go that way. So they're qualitatively very different motions which are separated by singularity. But for the most practical purposes, we will assume that things are smooth. Then, since Leibniz and Newton, our prejudice is to say that time is continuous, there is time. What happens in time? Point to study also maps where time is integer time. And I'll show that there is always a natural way of reducing flow to maps called concurrent sections. But if you just bounce a ball on the table, you might just record the times when the ball hits the table, and you can show that that's full specification of trajectories. Don't lose any information by that. So we'll distinguish continuum, and our intuition is because we are trained in Newton, Leibniz, etc., calculus, we are thinking that things are continuous, but we'll find it convenient to do either one according to what problem we're looking at. And there'll be just notational nuisance because various things have to be written. Stability has been studied in both cases, and people get confused between multipliers and exponents and stuff. Then what happens in time, if you start someplace in our state space, evolution in time, including this law, will give us a unique way to go someplace else by time x. And where we end up depends on initial condition in the elapsed time. And I'll refer to this curve that's left out in time, one-dimensional curve, as a trajectory. That's different from an orbit. So, again, this my usage in this particular book. Other people might have other usages. That the orbit will be defined as all the points you can reach for all times. So orbit of X O X E 0 for all times. By its definition, orbit is an invariant object because it's something that collects all the points reached for all times. So if you evolve any point on the orbit, you'll be just sweeping within that set. You don't exit this because it's a set of everything you can reach. So orbit is an invariant. So simplest example of an orbit is if you have a periodic motion, so you have something that goes someplace, comes exactly where it started. Then this orbit will not change in time. All that will happen is the little points will march on it. If I take any representative point of vector, the orbit will be an invariant set. Actually, the whole secret of the theory of static dynamics is to realize that the behaviors and averages and everything that need predictions that we need to get from the theory can be recast in terms of such invariant sets. It's not obvious at all, but that will be the main thrust.
So, is there an explicit time dependence on the governance rule, like the evolution rule?
Explicit time dependence on
the
law of evolution is immutable. Newton gave us the law and it's the same for all times. So the law doesn't change.
No, I mean.
So it's autonomous.
Okay, it's autonomous. Okay.
Yeah. So basically, we don't want to look at autonomous systems. If sometimes you look at periodically driven and so systems, which won't be a very hard step to take once you understand autonomous dynamics. The whole idea of dynamics is the space of state is God-given, the law of motion is God-given, and I'll figure out what happens. Usually we can write some equations down, but figuring out what they do is extremely hard. So this is, the way you think about how representative points behave. What happens when you take a state of the system? What will the law of motion do to it? You might also want to think about what happens if you take regions. You might take a set of initial states in a point that kind of. And then it turns out that continuum mechanics intuition is very useful. Things you know about moving things and deforming them. And it carries on to large dimensions. We have intuition about 3 dimensions. Often we'll define an initial set, MI, initial set, and we will look at what happens to it at the time of motion. So we'll have initial and home. And it'll turn out that thinking this way is actually absolutely necessary. That while it's mathematically impossible to in general to describe what happens to one particular point, one particular state, specified to infinitely many digits. Describing what happens to the regions, or what happens if you start in Alabama rather than Georgia or something. There'll be some very qualitative behaviors which will be very robust, and that will be another underpinning of the theory. So our strategy will be to, given the dynamical system, figure out what these invariant sets are, orbits, objects, and then give predictions in terms of these invariants. For example, in particle physics, once you're given a theory, you produce a spectrum of particles, the way they're killed, or they're called proton or something, and that's the content of the theory. Non-linear dynamics is kind of the same way. You try to find out coordinate invariant, independent representation of what's essential about the dynamics, and then once you can do this, there is a powerful machinery that gives you predictions.